Welcome back for our third mini lecture on Unit 8, which is stellar evolution. In this mini lecture we'll talk about the aging of sun-like stars. Now by sun-like I mean low mass stars, stars that are like the mass of the sun or less massive. In our next mini lecture we'll talk about stars that are many times the mass of the sun, and we'll find that their aging processes have some similarities but some differences. The material in this mini lecture is found in Chapter 20 in sections 1 to 3. If you don't remember our talks about the structure of the sun and how the sun produces energy and how the sun stays stable, you may want to go review the mini lectures for Unit 6 on the sun. But before we talk about stars, let's talk about cars. I recently bought a new car, a new used car. Let's suppose that I had an evil used car salesman, and right before he gave me the car, he filled the gas tank up and then welded it shut so that I could never put any more gas in the tank. How far would I be able to drive the car until it ran out of gas? There are two main factors that you could think of that would probably tell you how far you could drive this car. First of all, the size of the gas tank. The more fuel that I have, the further I can drive the car. But another thing that comes into play is the gas mileage. If I get great gas mileage, I could go a really long way. And if I have lousy gas mileage, even with a large tank, I may not be able to go very far. Stars are very much like this. Stars are producing energy by nuclear fusion, and we call their fusion process their nuclear fuel. And a star only gets one tank of fuel. Stars aren't, the sun is not constantly getting refilled by any outside gas cloud. So what will determine how long a star can live? Well, the size of the star's gas tank, which is the star's mass. How much hydrogen does it have to convert into helium and produce energy? And that's all related to the mass of the star, since all stars have about the same amount of hydrogen. The other thing, the gas mileage, for a star we're talking about the energy output of the star, or its luminosity. Every single fusion reaction produces the same amount of energy. The energy output of a star is what we call its luminosity. So the higher the luminosity of the star, the faster it's using its fuel. The smaller the luminosity of the star, the slower it's using its fuel. We combine these things and we can estimate how long a star can live. So let's do this. Let's start by looking at the sun. We know the sun will live about 10 billion years. That's what models say. So let's just call the mass of the sun 1. Let's call the luminosity of the sun 1. And let's call its lifetime, although we know it's 10 billion years, let's just call that 1. Doing this allows us to reference other stars to the sun. Now let's look at Rigel. Rigel is the knee of Orion the Hunter. And Rigel is a massive star. It has a mass 20 times that of the sun. So it has 20 times more fuel than the sun has. However, its luminosity, how bright it is 200,000 times that of the sun. Although Rigel has 20 times more fuel than the sun, it's using that fuel 200,000 times faster than the sun. And so if we calculate its lifetime, we take, 20 times more massive divided by using it 200,000 times faster, we find that Rigel's lifetime will be 1/10,000th that of the sun, and if you again do your calculations, that's only 1 million years. That's not very long. There's also a faint star, so faint we can't see it, but it's the second closest star system to our sun. We've got our sun, then there are 3 stars in Alpha Centauri, and then the next closest star is Barnard Star. Now it is a low mass star. Its mass is about 1/6 the mass of the sun. Luminosity wise, as I said, it's extremely faint. It's 1/300th the luminosity of the sun. So you take that mass, it's got less fuel than the sun, but it's using it much more efficiently than the sun, doesn't need nearly as much of it. So the lifetime of Barnard Star ends up being 1/6 divided by 1/300th, or 50 times the lifetime of the sun. So the sun lives for 10 billion years. Barnard Star will be able to shine for 500 billion years. Really long time. This relationship holds true for all single stars in the sky. As you go more massive, the lifetime of the star gets shorter. And as you go to less massive stars, less massive than the Sun, they live longer and longer, and the lowest mass stars will have the longest lifetimes. Let's now look at the inside of the Sun. Here's a plot on the right of if we just measure what the Sun's made of. When the Sun was born, it was about 75% hydrogen, the rest helium, a little bit of the heavy stuff. We're not going to worry about the heavier stuff right now. So mostly hydrogen with a little bit of helium. And this mix was the same all the way through the star. But now when the Sun began nuclear fusion, at its core it starts converting hydrogen into helium. So it's using up the hydrogen and making more helium. Further out, when you get outside the Sun's core, it's not doing nuclear fusion. So it still has the same amount of hydrogen and helium. The Sun's not mixing that extra hydrogen down into the center. Over time, the Sun will finally use up all of the hydrogen at its core, and in another 5 billion years, the Sun will have no hydrogen at the core and only have helium. But meanwhile, up at the surface, the Sun is still 75% hydrogen and 25% helium. There's no mixing to bring that extra hydrogen down in. So once the Sun has used up all of the hydrogen at its core, nuclear fusion can't continue to happen at the core of the Sun. So remember how the Sun regulated itself, why the Sun stays the same size and the same luminosity. If fusion started to happen too fast, the core would heat up. This higher temperature raises the gas pressure. That pushes out against gravity. That expands the gas. Expanding the gas cools it. Once it gets cooler, the fusion slows down, and we sort of self-regulate it here. If fusion's too slow, if there's not enough fusion, the core begins to cool off. This cooler gas has less pressure. Gravity squeezes it inwards. That raises the temperature, and fusion will begin to pick up again. But when the Sun runs out of hydrogen at its center, fusion will begin to go too slow. In fact, way too slow, because there won't be any at all. The core will begin to cool off slightly. This again lowers the pressure, and now gravity will begin to shrink the core to pull the gas inward, raising the temperature. But now fusion doesn't pick up because there's no fusion to happen. There's no hydrogen around to fuse. So gravity will continue to pull the core inward, making the core hotter and hotter and hotter. This thermostat no longer works. This helium, which is sort of like ashes of the Sun, gets squeezed downward and gets hotter and hotter. Outside of the core of the Sun, we still have hydrogen. And so the region immediately surrounding this helium ash can still do nuclear fusion. So the Sun doesn't die, it doesn't instantly go out. It's just that now the fusion is happening in a shell around a core where there's no fusion happening. This is a different arrangement than the Sun has now, and the outer layers of the Sun respond to this different arrangement by fluffing outward. So the outer part of the star begins to grow and expand, even as the inner part of the star is shrinking due to the pull of gravity. When all this happens, the Sun is expanding, so it cools off as the gas expands. But in that shell, because the temperatures are pretty high, fusion happens at a really fast rate. And so the Sun will get brighter. So it'll get cooler on the surface, but yet put out more energy, get brighter. It's turned into a red giant. When the Sun becomes a red giant, it will swell up to almost 100 times its current size, which is more than enough to swallow Mercury and Venus. So as the Sun gets bigger, those two planets are gone. So visit them now. 5 billion years from now, they're gone. The central part of the Sun, this helium, at first it doesn't do any fusion, but helium can begin fusion if it heats up to 100 million degrees. That's 7 times hotter than the Sun's current temperature. When you heat it up to 100 million degrees, 3 helium atoms can fuse together to make carbon, and that releases energy. So when the red giant's core is squeezed enough that it gets this hot, nuclear fusion can begin again, but now it's a different type of fusion. Instead of turning hydrogen into helium, we're fusing helium into carbon. And at about the same temperature, if you have carbon and you have helium, they can fuse, release some energy, and make oxygen. We call this helium fusion, and helium fusion results in a mix of carbon and oxygen. So now we have fusion in the core of the star again. We still have hydrogen fusing into helium in a shell on the outside of this core, and then we have the outer envelope of the star. This looks sort of like the sun today. Fusion in the center of the star, nothing happening outside the core. And so the star will yet again adjust and rearrange itself. It'll shrink a little bit, not a lot, but some. It'll get a little hotter when it shrinks, and it shrinks down to something we call the horizontal branch. So here's our Hertzsprung-Russell diagram. The sun started off on the main sequence. It became a red giant. As soon as helium fusion begins, it rearranges itself, shrinks, becomes a little hotter, and gets on this thing called the horizontal branch because it's kind of horizontal in the Hertzsprung-Russell diagram. So things on the horizontal branch, stars on there, are sun-like stars that are fusing helium into carbon and oxygen in their core. They're still doing hydrogen fusion into helium in a shell outside the core, and then further out from that, the star is too cool to do any nuclear fusion, so you still have mostly hydrogen and helium. Now the carbon and oxygen won't do any further fusion, so once you have a core of carbon and oxygen and you run out of helium, fusion will again stop in the center of the star. And again, just like before, gravity will pull it inward, and you again have fusion happening in a shell, this time two shells, outside the central core of carbon and oxygen ash. And so we have another situation similar to like the first red giant, and the sun will swell up again, become even bigger than it was before, and the outer layers cool. It'll still be really bright, so it becomes a red giant again. This is called the asymptotic giant branch. Don't worry about the name, it's just a second red giant. So sun's on the main sequence, becomes a red giant, begins helium fusion, shrinks down to this horizontal branch. When it runs out of helium to fuse, it grows into a red giant again. And at this point the sun will be 200 times its current radius, which is large enough to swallow the Earth. Now, whether or not the Earth gets swallowed, it's kind of hard to say, because at the same time the sun will be losing matter. We'll talk about that in a second, but as it loses matter, its gravity gets weaker, and so the Earth will move further away. Some simulations show that the sun will swallow the Earth. Other simulations show that the Earth will move out enough that it'll survive, though the surface of the Earth will still get hot enough to turn it into lava. We won't be living here at this time. So here's what the surface of the Earth might look like during this second red giant phase of the sun. Pretty bad day to be outside. Now we have a red giant again, carbon and oxygen in the core, not doing fusion, helium doing fusion outside it, hydrogen doing fusion outside that, and then the outer layers of this red giant too cool to do any fusion whatsoever. So you say, oh, maybe the same thing will happen. Maybe gravity will squeeze the carbon and oxygen until it can begin some sort of fusion.